All right, welcome to lesson 2. So we're going to talk about algorithm design and algorithm analysis. So before we talk about algorithm design and algorithm analysis, let's do a little bit of housekeeping from lesson 1. So in lesson 1, we talked about what data types we're going to be using. And I said, hey, we're going to be using these data structures. And I talked about different data types, and we talked about an array, a list, a tuple, an integer, a float. So I talked about these different data types. And those are all different data types, but a couple of those data types are also considered data structures. And you say, well, wait a minute, how can a data type be a data structure? And yes, it can. They can be data structures if they contain data that is multiple pieces of data. So let's go look at, there's a concept of physical data structure and logical data structure. So an array or a list, when we look at it, they look almost identical. The difference between an array and a list is a list can have just about anything you want stored in any one of these little indices. An array, it's all the same data type. So a list, these can all be different data types. The fact that this is sequential, it's a structure. It's not just a single value. An integer, that's just a single value. That's a data type, and there's an instance of that one data type. Can't consider an integer as a structure. An array is both a data type, it's a class that defines what the array is. It has functionality or methods that allow you to interact with it. And it has attributes associated with it. And it holds in it integers or floats or strings. So that makes it both a data type and a structure. So it's physically a data type because we're storing data in these little memory locations. We have other data structures that are logical data structures. They're not physical data structures. So an array is a physical data structure. A list is a physical data structure. There are data structures like queues. A queue is a logical data structure that uses a data type to do what it needs to do. And we'll talk more about those when we get to them. When we get to the different data structures, we'll talk more about them. But I wanted to differentiate between what's a data type and what's a data structure. So the data types are built into the parent class, or I should say, the built-in library within Python. With the exception of the array, and that's an add-on. Now, There's a difference between data type and data structure. And if you went and did a search, you would find it. I did it just to see how many different perspectives. And I looked at so many of them, and some of them I totally disagree with. This one says, well, there is no real difference. Well, there is, but it's narrowly defined. Data structure is a specialized format of organizing and storing data. I like that one. I like that one. So let's jump back over here. We're going to be dealing with algorithms now. And once we get through algorithms, then we'll look at algorithms as they are applied to the data structures that we're going to explore. So now, when we're going to deal with algorithms, let's think about where did algorithms come from. Algorithms were around long before computer programmers. Algorithms were around back when it was just the mathematicians. So algorithms, depending on the textbook that you're using, and when I think about algorithm analysis and design, what's considered the go-to, or what I think is the most widely used textbook, is Introduction to Algorithms. It's Corman, Leeserson, and Rivest and Stein. And those authors wrote the book, if you will, on algorithms and algorithm analysis and design. They wrote it from the perspective of a mathematician. Now, I'm not a mathematician. I'm a programmer. I'm a data analyst. I have to be able to look at things both from the perspective of the mathematician and the programmer, because we're walking a fine line with what we're looking at today. Algorithms from a mathematical standpoint, when we go to analyze them, we start counting at 1 and go up to n. N being this arbitrary number. It doesn't matter what it is. I don't know what it is. We'll just say it's n. So I'm going to go from 1 to n. As a computer programmer, we start counting at 0. So I go from an index of 0 to n. And if you go on to another course, or if you go on to a course that utilizes that textbook that I was speaking of, it can be a struggle for many people, switching back and forth from the perspective of I start at 0. No, you start at 1 now. If you're going to code it, you start at 0. But if you're going to analyze the algorithm, you start at 1. Man, this is killing me. We just need to understand that algorithms, they really started as mathematical computations. What was the math we had to do to come up with a result? We had input, we did the math, we came up with a result. That in-between part where we did the math, that's the algorithm. And then you got into an intro to programming class, and they said, all right, you need to understand an algorithm. Somebody said, what's an algorithm? Well, it's kind of like, it's kind of like a recipe. How do we go through step by step to make, let's say a cup of tea? Pour water in the pan, put the pan on the stove, light the stove, step by step all the way through, and that's the stuff you got to do to make your cup of tea. That's an algorithm. Ish. In a way it is. It's an overly simplified form of an algorithm, but it is a form of an algorithm. For what we're going to talk about, we're going to look at things from both perspectives. From, it's like a recipe. It's a calculation. We're looking at all of it. So our program takes input, It processes everything it has to work with, does whatever it's got to do, whether it's a recipe, a calculation. We got to do what we got to do as programmers to come up with the deliverable, the output. This P part, the processing in IPO. This P part in the middle, let's look at that as our algorithm. And I want to understand how efficient this is when it comes to n. So this input of n, I don't know how big n is, and it shouldn't matter. But if n gets really, 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 really big, will that change the efficiency of this algorithm? Does this algorithm get really, really bad? So if I had two algorithms that did the same thing, and one of them got horrible when n was huge, and one, it wasn't so bad. That's what we're looking for. That's the gist of what we're doing, is being able to look at the algorithm and say, all right, if n got really, 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 really big, is that going to crush our algorithm? Is our algorithm going to be ridiculous? Now, I mentioned in lesson 1 an algorithm that I proposed I was going to use, and the professor's like, "You sure you want to do that?" I said, "Yeah, it's a pretty algorithm. I like it. I like the way it's laid out, and yeah, that'll work. It's effective. It does what it's supposed to do. Is it efficient? No, not with the computer I was working with. It would have taken 164 years. Now, that was just because of the resources I had available. Had I had access to a better computer with more processing capacity and more RAM, it wouldn't have taken 164 years. I could have gotten the work done considerably faster. Was it still fast enough? Is the cost too high? That's the things we need to understand with what we're doing in this course. Okay, so we're going to take an input. I may know the number, I may not know it. I may just treat it as an n. We're going to do what we do to it, and then we're going to come up with an output. How efficient and how effective was what took place. That's it. That's what we're looking at. So as we go through this, we're going to look at time complexity. The time complexity, the form of time complexity that we're going to deal with is called big O notation. And essentially, we're looking at what's called asymptotic notation. We're looking at things, it says here, that depend on the input size. The input size, we're going to say, is n. And as n increases, generally we're going to see runtime increase, meaning the time it takes to do the work. Well, does n increase relatively in a slow increase, or is it a dramatic increase? Is it an exponential increase? If n increases by 10, does time increase by 100? Wow, that's huge. It's possible. What if n increased by 1,000, but time only increased by 1? Well, that wasn't so bad. And those are the things that we're going to look at relative to time complexity. But we've got to be able to go through and analyze the code and put a cost associated with it. So here's a block of code. And I say, if n is equivalent to 0, or n is equivalent to 3 print data. Well, how many times are we going to go through this? If I start here, if I start before this block of code, say I start up here and I'm going to work my way down. So I'm here, I'm on that line of code. That line of code right there, how many times am I going to run that line of code? Once. It doesn't matter how big n is, I only do this once. I have no repetitious structure, there's no loop, I just did it once. How many times am I going to do this? Well, I'm going to do it if and only if, so just once, because there's no repetition in here. And now I get down here and I say else for I in range, ooh, now we've got some unknown. This is where it can get kind of squirrely. I don't know how many times this loop is going to run for, it says n times, and we'll say n because I don't know how many times it's going to run. The verbiage here, the fact that they used n here and n here, that's, but we don't know what the rest of this line of code is, but this line of code is an unknown number of times. So if I had said, hey, I'm going to go through this 3 times, I only go through that 3 times, it doesn't change regardless of n. So that would be constant. So this C here is the cost. So I can go through and say, well, the cost associated with this, constant. Cost associated with this, constant. How many times do I do this? Constant. Doesn't change with n. For I in the range, ooh, this could change. This would potentially be n. This, n or less than n. N, we'll say n. I'd prefer to have this something other than n, say I. If I is blah blah blah, go. Or C is equivalent to 0. Not pretty code, but we're looking at the cost. So we essentially, if we're going to analyze this, we go line by line through the block of code to analyze the cost. Let's say cost, the time required. How much time does it take? Does time change? Oh, that's constant. That's constant. That's constant. Ooh, that's a loop. That depends on the range of what? How big is that range? That can get big. So that's not constant. That would be n. The next one is going to be n because it happens in there. So this one, in theory, the way that it's implied, it's not complete code, but the way it's implied, would be a runtime of n. So there it is, n. And I say that it would have, worst case scenario, it will run n times. Best case scenario, I would run once. So if n was 0, I would run. So this should have something in here that says for I in range n and close off the parentheses. If n was 0, I run through it one time. If n is 3, I run through it one time. That's best case scenario, was once. If n is anything other than 0 or 3, now we're getting into worst case scenario. Well, how bad can it be? Well, how big can n be? And depending on how big n is, will dictate how much time is required to perform whatever it is we got to perform. Now, there's not a whole lot of work going on here. There's not a lot of processing happening. Depending on the algorithm, this is our algorithm. That's the processing. That's the work that's taking place. It's not a pretty recipe, but that's our work. That's what we're analyzing. Depending on the algorithm that we're dealing with, it could have a lot of work taking place, a lot of processing requirements. Uses a lot of calculation taking place in there, embedded processes. If I had another loop nested in this one, I run n, and then I get into this other one, and I run it n times potentially. Now we're looking at n squared. Now the time complexity, as n gets bigger, man, that can get really ugly. And this big O notation allows us to go through and look at it. And we're looking at the worst case scenario, or the worst case running time. If n was 10 billion, how bad could it be? It could be this. Well, what if n was 3? Be nothing. And it would run fast. So we've also got the average case running time, where we look at what's best case scenario. You just go through it once. Worst case scenario, depends on how big n is. And the average is somewhere in between. Somewhere in between. I don't hope for the best. I don't want to plan for the best when we're talking about how this thing's going to run. Big O notation, we're looking at how bad can it be? Is it going to take 164 years to run this code? It could. It's okay. Now that I know that, I want to plan for that being what actually happens, and I don't want to choose that algorithm. I'll choose something else that's not going to put me in that situation. So that's runtime complexity. Space complexity has to do with how much RAM we're using to perform what we're doing. So let's say that n is n's the length of a list. And I've got a list that is 100 in length. It goes from 0 to 99. I've got another list that goes from 0 to 10 billion. And I need to read that data into the computer. I need to put it in RAM so that my processor can use it. Which one's taking up more RAM? Yeah, the one with a really, really big N. So that's where the space complexity comes in. Because for us to process this data, we need to store it in short-term volatile memory, which is our RAM. And if you store all of your data and you use up all of your available RAM to store that list of a length n, you don't have any more RAM to use for the incidentals to actually keep the computer running and deal with all the other little things that may happen. So space complexity is a big deal. So we look at space complexity the same way. We're not going to focus on the space complexity in this. We're going to focus more on the time complexity. And when we look at asymptotic notation, we're looking at the rate of growth, the order of growth, as n becomes really, 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 really big. How long is it going to take if my list is a length of 100 compared to my list is a length of 10 billion? How is that going to impact? How is that order of growth going to impact my time complexity? We look at it 3 different perspectives. First one's theta notation. That's that symbol you see right there. The next one's going to be big O notation, which is worst case scenario. We'll say worst case runtime. It's the upper bound. It's not going to get any worse than that. It's just as bad as it's going to get. Theta notation is worst case, but you're kind of hoping for the best. It's not quite middle of the road, but it's not horrible worst case scenario. So it's got a tight bound to it. And then we can come down, and there's big O. And then we've got omega at the end. And omega is best case scenario. What happens? So, well, wait a minute. I want to know what best case scenario is, but I can't expect the best case every time. So when we look at time complexity, this is all big O notation. We don't see the theta and we don't see the omega. We see the O. So big O with a 1 in parentheses, that's constant runtime. It doesn't change. There is no real n impacting it. Every time I run that algorithm, it takes the same amount of time. The input doesn't change. The size of the input, n, doesn't have any impact on it. This one is O to the log of n. It's a logarithmic growth rate. And when we look at these curves, we'll see those curves relative to what we're at. So constant, that's a flat line. It doesn't change. A logarithmic, it starts to grow, but it's a real slow growth. Linear, we're going diagonal. Linear logarithmic, we're going up even faster. Quadratic, meaning big O, n squared. So you should have a hat in there. So if you see n with a hat, it's like an arrow in between the two, pointing up, and then the 2, that means n squared. That's drastically faster growth rate in time complexity, the amount of time used as n gets bigger. A cubic, or n cubed, n to the 3rd, that goes even worse. And then when we say 2 to the n, I don't even know what that exponent is. It'll be 2 hat n. That one's jumping way up, and then it gets even worse beyond that. We may see an exclamation point, and that's something that's beyond the scope of what we're going to deal with. And when I talked about the other course, if you have to deal with that textbook, Introduction to Algorithms and digging deep in algorithm analysis design, you would deal with a broader perspective of time complexity and big O notation, and literally break it down and analyze one algorithm after another mathematically and saying, well, what's worst case scenario for this? Now, how this is presented in the book, some of it I'm not real thrilled with it, but I'm looking at this book from so many perspectives and not just nitpicking little things here and there. Now, with this, I mentioned before, if we had nested like this, to where time complexity for this, that's n. The fact that it's nested, now we're at n squared. Worst case scenario for this is n squared. What we see here. So that's our big O notation. Worst case runtime for that algorithm or that block of code is big O n squared. It's quadratic growth rate. Doesn't mean that that's what it's going to be. So if n is 10 billion, then that means 10 billion times 10 billion. That's our worst case scenario. How many times this is going to have to go? What if n was 1? Yeah, that's not so bad. But I can't expect best case scenario. I have to expect this worst case scenario on this. So as we go through it, they explain, we can go through and we look at, here we are here, say what's worst case scenario? This one's n to the third n squared. So this one, I'm looking at n to the third n squared. So this is true, it's not equivalent to n squared. N to the third is worst case scenario. Worst case scenario. Worst case scenario. So it's not difficult to see what worst case scenario is when we go and glance at it. So if somebody gave you, said here's the upper bound, or here's the formula for it, what is the notation? It's not difficult to see. Time complexity of n of 2n plus 7, that's n. Whatever n is, that's worst case scenario. If it was 2n squared plus 3n minus 7, then it's n squared. Omega, we go through and we look to see what's best case scenario. And yeah, it matters what best case scenario is. You know, we hope for that. But that's our lower bound. That's the best that can happen. All right. So when we go through and look, if it had, let me see one that's not written so bad. All right, so in here, say there's our notation. N squared, n squared. The best case scenario is n squared. Best case n squared. Best case n. And we say best case sigma n. Big O-N, worst case. So we're going to have to go through and look at and understand this. So when I see this nested, I know I'm dealing with n squared. It is what it is. And I can go through and run the math out and get an understanding of what's taking place. So I've got a function of n. This runs n times. This runs n times n times. So this is n. This is n squared. Worst case scenario, n squared. So of all the things that happen, which one takes the longest amount of time? How bad can things really get? And we just go through and analyze step by step. The cost of doing this, n. The cost of doing this, n squared. And we can go through and do the same analysis, block by block, of different code. And it's the same thing as we go through it. In this lesson, I'm introducing you to algorithm analysis. You've got some time complexity that go through and look at these exercises. Look at these little snippets of code. You're going to have a quiz where you're going to have to go through and do some algorithm analysis and come up with what's the time complexity. Is it, you'll got multiple choice questions, and you'll go through, scroll up here, which is it? Constant, logarithmic, linear, quadratic, cubic, what is it? So you'll see a block of code and you've got to go through and figure out what's the time complexity on it. How bad could it get? One of the other things that you're going to do in this module is a discussion about time complexity and why we worry about going through and doing this. Okay. So with that said, knock out that time complexity assignment. It's the little quiz. Knock that out. Get your discussion out of the way, and then you'll have a reflection to take care of at the end. As always with the reflections, take time and reflect on what worked for you, what was difficult, what did you need help on, so that your instructor can go through and look at those reflections at the end of each lesson and see where everybody stands and what adjustments need to get made to your individual instruction, maybe tutoring, whatever it may be, or maybe an adjustment we need to make to the course as a whole. So see you in the next lesson.